Hey kiddos, so really quickly, let's just as a group recap what we've learned so far about these types of reactions and do some demonstrations as well, okay? So in your Nearpod, you've already learned that we have 4 classifications of those chemical reactions that help us understand what's going on a little bit more, and also we can make predictions because science is all about making predictions and understanding why the world works. So the first one is synthesis. Remember, this is when we have 2 or more substances combine and they form one compound at the end of it. So a good way to remember how these type of chemical reactions are by using shapes. That helps us kind of visualize what's going on in this chemical reaction. So we have our circle. In this specific instance, our shapes can either represent different elements or different compounds, okay? So in a synthesis reaction in general, though, you have your circle and you have your square. They're separate, they're not together, and when that chemical reaction occurs, that's our arrow, they end up bound together in a molecule. So you have 1 plus 2 equals 3, or you can say A plus B equals AB. Another way to say it is circle plus square reaction, you have your circle square bonded together. So it's pretty simple. Every time that you see 2 or more reactants, remember reactants in products, you have 2 or more reactants over here. At the end, your products, you only have 1. Remember, because this molecule is all bound together. Let's look at some examples of real-life examples of synthesis reactions. So our formation of our table salt. We all love salt. So we start with Na plus Cl. Remember, you have your Cl2, that's your subscript. So you have to balance it out with your coefficient. So 2Na plus 2Cl yields 2 NaCl. If they're together like this, they're going to be bound together. And then we have our 2 there, so our law of conservation of mass is followed. Again, 2 reactants, 1 product. We also have everybody's favorite, let's make some water. So here's the water synthesis reaction. We have 2 H2s plus an O2 yields 2 H2Os. So what I have, and hopefully one year we will be able to use them. Unfortunately, we can't use it this year because of germs, but I have these molecule kits, which are really awesome, and I really like to use them. So it helps you visualize. So right here, these little, they look like one of those the dumbbells that you work out with. These actually represent your 2 H2s. So you have your coefficient here that's telling you you have 2 of whatever follows it. Your H2, that shows that you have 2 hydrogens, which are represented by these white balls, that you have 2 hydrogens bound together. So here's the H2, and because I have 2 of them, here's my coefficient, I have 2. So that's what that H2, 2H2, this represents our H2. Now our O2, we don't have a coefficient, so that means there's only 1 of them, but we do have that subscript 2. So right here, I have 2 oxygens that are bound together. So these are my reactants. 2 H2s plus 1 O2. 2. Altogether, I have 3, right? But our pluses together because these aren't bound together. So my reaction is going to be to form water. So remember, all chemical reactions is just making and breaking bonds. So I know that at the end, I want to have 2 H2Os. So I take my little bonds and I break them and I reform them to form water. So here is one of my waters. And if I do this, all I'm doing is just making and breaking bonds right now. I have this one and have my second water. So I yield 2 H2Os. I've combined these 2 together and I've made something, synthesis, to make. I've made 2 waters, H2O, and I have 2 of them, so there's that right there. So that in and amongst itself is a synthesis reaction. Pretty straightforward, pretty common. Moving on to, if we have synthesis, if we build things up, we need to be able to break things down. That's another type of reaction. So we have over here our decomposition reaction. Remember, like I said in the Nearpod, I want you guys to think of real life examples to help you understand science. Don't just memorize. So when it comes to decomposition, think of when you've heard decomposition in other places in your life, right? If a flower dies outside, it decomposes back into the soil. It breaks apart. Decomposition reactions, we're breaking things apart. So again, let's go back to our shapes. We have our circle square bound together or bonded together. Our reaction takes place, it busted up. So now we're back to our circle and our square independent of each other on their own. That's a decomposition reaction. If you look, it's opposite of the synthesis, right? So our decomposition, we're busting up what we already made. So let's go back to our good pal, water. So I have, because in my synthesis reaction, I just made 2 waters, but now I want to decompose those 2 waters. So here I go. I have my 2, we're looking at this formula right here. I have H2O. I have 2 of them, 2 H2Os, and I want to decompose it now so I can go back to 2 H2s and an O2. So again, just like everything else that we've done so far, these chemical reactions are making and breaking and rearranging chemical bonds. So I have one of my H2s right here, but I know that I need 2 of them. Luckily, my law of conservation of mass is holding true. I have 2 to give, 2 H2s, and then I go back to my O2, which is bonded together oxygen to oxygen this way. So I just decomposed it from my 2 waters back to 2 H2s and an O2. See how simple that is? We're starting with one reactant and we are busting it up back to its components. Now, this doesn't necessarily have to be, decomposition doesn't have to be broken down back into elements. You can decompose larger molecules like this, which is hydrogen peroxide. We talked about that in class. If you pour it over a wound, it fizzes. You can break down or decompose hydrogen peroxide back to water and O2. So water itself is a compound, but you're still busting up that one molecule and you are leaving yourself with several products. One reactant, several products, still a decomposition. It doesn't necessarily have to be broken down back into elements. You can break it down into smaller molecules. Okay, so that right there, that's how we represent synthesis and decomposition with shapes, and those are some real life examples of them. Now, let's move on to where it starts to get a little bit trickier, because we have our replacement reactions. Now, remember, we have 2 different kinds of replacement reactions. So replacement is the category, and then we have 2 different types that I want you to know. The single replacement, one element replaces another element in a compound. Pretty straightforward, pretty easy, pretty simple when it comes to this. So let's go back to our shapes, right? We always want to go back to our shapes. We have our molecule, our circle square bonded together. Then we have this triangle. This triangle is going to represent a new element that wants to come on in and form a bond. So what happens in our reaction is the triangle replaces the square. So it yields our new bond of circle triangle, and then it kind of pops off that square to be on its own. So the triangle replaced the square in the bond, and therefore it got kicked off. Let's look at some real life examples of it. We'll start with this one. So this molecule right here is called silver nitrate, plus, we all know this one, copper. So if you add silver nitrate and copper together, that copper is going to bust off that silver, and you are going to be left with copper nitrate plus 2 silvers. That copper took the place of that silver and popped that silver off that way. And here's another easy one where let's see, it's iron this time is replacing that copper. So we have the Fe plus the CuSO4. Our reaction happens, that copper is busted off, that iron is replacing it, so we have FeSO4, and then the copper is left on the outside. Okay? Double replacement, kind of the same thing, except rather than that one element being on its own, and where we're left with a new compound and then a new element, we are going to be left with two completely new compounds. So back to our shapes. Here, I'm going to do this so that way we don't get confused. Back to our shapes, we have our circle and our square. That's one of our compounds. Then we have another one, triangle and star. These shapes can be anything. They're just meant to represent, to help you understand the types of reactions. It doesn't really matter what you make the shapes. They're more of a representation or a symbol for what our reactants can be. So we have these. What's going to happen is the square and the star, they're going to replace each other. There's two of them, double replacement. They're replacing one another. So we have our reaction, we have our reactants, reaction, then our products. If you see how it popped off, we now have a circle and a star and a triangle and a square. Two totally new compounds were made. However, remember, law of conservation of mass, we're not making new elements, we're just making new compounds. We're breaking and remaking bonds. Let's look at some. So we have our NaCl, we have our salt, then we have our silver nitrate, AgNO3. What's going to happen in this reaction is our silver and our sodium are going to switch. They're going to double replace each other. So then we're left with sodium nitrate and silver chloride. Everybody see how that works? Double replacement. And then we have another one with hydrochloric acid and iron sulfide. And again, that, the hydrogen and the iron are replacing each other. Double replacement. In single replacement, you're only replacing one. All right, guys, so I hope this helped. At the end of your Nearpod now, you are going to take a little quiz and see how well we are understanding these types of reactions so far. All right, kiddos.